All right, it's my pleasure to introduce Melissa Sherman-Bennett from MIT, who will talk to us about cluster structure on type A braid varieties from 3D plabic graphs.
Thanks for the opportunity to speak. It's a pleasure to come across the river, be here for a little while. So yeah, the work I'll be talking about today is joint with Pasha Galosh and Thomas Lamb and David Spire. We just posted a paper to the archive, and my slides are available on my website under the talks link. Okay, so today I'm going to be talking about some varieties, these type A braid varieties. And I'm going to be talking about a particular combinatorial structure on our coordinate rings. So that's what this cluster structure is. And the underlying combinatorics that's governing the coordinate rings is going to be something called 3D plabic graphs. So I'll tell you about what these are, but they're little pictures that look like this. Okay, so I'm going to start by talking to you about what type A braid varieties are, and then I'll say some words about what a cluster structure is, and then I'll kind of dig into this combinatorics. Okay, so first, to talk about these braid varieties, I need a little bit of background on flags. So this is a type A talk. So my G is always going to be SLN here. B is the subgroup of upper triangular matrices. And as usual, I'm going to identify the quotient G mod B with the complete flag variety. Okay, and I guess just to be really concrete about my conventions, if I have some coset GB, that shows up, then the way I'm going to get my complete flag from this is I take the first vector, sorry, the first column of G, I take its span, that will give me like the one-dimensional element of my flag, and then the span of the first two columns, that will give me the two-dimensional subspace there. Okay, so I'm going to need the notion of the relative position of two flags, which very roughly is just going to tell you how different two flags are. This is the relative position will be a permutation. So first, the simplest situation is if two flags are in SI position. So SI is just a simple transposition. So F and F prime are SI related if these two flags differ in exactly the ith subspace. Okay, so not too complicated. You can also translate this notion into some statement about coset representatives if you prefer that. I don't like to think about it that way. And so, okay, so more generally, two flags F and F prime are W related if, well, some coset condition holds, or I like to think about it this way better. They're W related if for every choice of reduced word for W, there's a sequence of flags which interpolates between F and F prime, and the word for W that you pick is going to dictate how you change subspaces along this path. So to move from F to F1, I change the I1 subspace, where SI1 is the first letter in my word, and then to go from F1 to F2, I change the I2 subspace, etc. And I'm supposed to start at F and go to F prime. So that's what being W related is. And I guess from this way of thinking about it, it's not obvious that any two flags should have a relative position, but in fact they do, which you can see from thinking about it like this. Okay, so that's relative position. And I'm going to use this to define these braid varieties. Okay, so the braid varieties, so they're denoted X beta underline U. So they're indexed by this pair. The first element of my pair, beta underline, is a word in simple transpositions. So it's not necessarily a reduced word, it's just some arbitrary word in the reduced, in the transpositions. And then the second element of my pair U is some permutation that shows up in the beta underline extraction. So I need to be able to find a reduced expression for U as a subword of my beta underline. Okay, so you give me these two pieces of data, beta underline and U, and I will produce for you a variety. So points in this variety are going to be walks in the flag variety. They're walks that start at the standard flag, so they start at B. And then the steps in my walk, the directions will just be dictated by my word beta underline, right? So my first step of my walk, it has to be in direction SI1, the second step in direction SI2, etc., all the way up until I get to my last flag. So that's how the choice of beta underline plays in. Now, what does U do? U is going to constrain what my final flag in my walk can be. Or
You did.
Oh, no, yeah, you brace the projector, I guess. Okay, here, let me try doing this. What's happening? Oh, wow, this is very suspenseful.
Yeah, I see.
I'm gonna put D.
Okay, I'm gonna,
Restart.
yeah, there's a restart button on this thing.
Okay, well, maybe I'll unplug it and restart. Let's see it. Technology.
Yeah.
You run over your tablet or the system?
That's the system. This tablet is an iPad and it's not plugged in right now. Yeah. I guess, a backup plan is that,
Are you fully?
yeah, I'm on Zoom right now, so everyone in the room, I guess, could join the Zoom meeting.
Yeah,
and see
we
my
also have this other thing too. This thing Hunter has used successfully. I think you could plug it in with an HDMI.
Okay, and so the actual,
Yeah.
it's just small. Okay.
Yeah.
Oh, okay, well, tonight,
Well, something.
Started?
Okay, okay.
yeah, I have plugged in, I think. I'm not sure if it knows. Please plug the HDMI cable into the device. Okay. It is plugged into my device. Is the HDMI cable plugged into the? Adapted them just fine. Let's see, I guess maybe we can see if I.
Yeah, and someone just trying to say, it'll take some time to turn it on. If you go get a cable out. I'll just think. Just like turn it on and push it.
Yeah, I can, since I did,
Yeah, I think Hunter,
I think I might have to wait one of you.
Yeah, that's okay, I hope it's not that my adapter just suddenly died. It's very unfortunate. I guess. I also have my.
So actually, I didn't plug in when I used this before.
I see, it's connected wirelessly.
Can you try to airplay, maybe airplane so you can see it?
Somewhere in that book.
And then use this thing, it could be a type C input, the other of this is it on the other side, and then there should be a button for the select wire. Probably on the other side, on the far side, on the side. Or at least it wasn't a big one, actually, no, it's on the bottom. I can come up here. Yeah, this is the HDMI. Here's the USB-C. And then, so you, well, let's see if it works, yeah. You have HDMI?
Yeah, I have even USB-C cable, if that would.
Yeah, we can get out there, so let's see. But where's the, this is it, what? This is the USB-C, I look on the side of the bottom. There's the plug here, big C.
That's it.
You're very prepared. Let's see.
Almost actually.
Yeah, how this.
It's very small, so it might be relatively difficult to see.
This is for the.
USPC was one.
Yeah, it seems like that was longer.
No.
The other option is possibly I can just join. If I could,
Yeah.
show you my
And
computer.
then share your screen with,
Yeah. Sorry about this.
no, this used to happen, actually, before they redid the technical room, it happened a couple of times, we had a mini match in the room.
Maybe you could let my computer into the Zoom room and I can see if I can share it from my computer.
Recording in progress.
It was just like the input got nudged a little bit and then it freaked out.
It tells us about some walk that we're allowed to take in the flag variety. Those walks will be points in the braid variety, but it is not just that we have, and we're not just looking at any walks with like this dictated pattern of steps. We're going to constrain a little bit where the walk ends. And the way we're going to constrain it is this final flag needs to be in position W, not U, with the anti-standard flag. Okay, so this looks like a very funny condition. There's other ways to get a variety like this. We do it this way to make connection with some other varieties called Richardson varieties. This is the way to set it up if you want to make the easiest connection to Richardson. Okay, so those are our braid varieties. And you might be wondering, well, why are they called braid varieties when I have not yet introduced any braids? The reason for this is that if I take my not necessarily reduced word and I do braid moves, so I commute simple transpositions that are far away, or I do like the 3 to 3 move, my variety, well, they're going to be, those varieties will be isomorphic. So I may as well, instead of indexing my variety with this particular choice of word and a permutation, I may as well index them with a positive braid beta and a permutation U. And if you don't know what a positive braid is, well, it's an element of the positive braid monoid. This is exactly like the symmetric group, except I've removed the condition that SI squared equals the A. Okay.
The isomorphism between X beta and beta prime or gamma, that's canonical?
Yeah, or so I guess there's a nice way to embed, okay, so this is affine, and there's a nice way to realize it as an affine variety. And if you are sort of insist that you're actually viewing all of those as affine varieties with this kind of particular embedding, then, well, this isomorphism is very natural. I'm not totally sure if it's canonical, but it's not hard to write down. Yeah. Okay, so what can I tell you about these varieties? So like I said, they're affine. They're also smooth and irreducible, and their dimensions very easy to compute. It's just the length of beta minus the length of the permutation U. Okay. So those are the varieties we're interested in. Why would we be interested in these? Well, there's a couple of really nice special cases, and that's probably, I guess, why. So if you're in this, okay, so the nice special cases are these. If you're in the situation where your beta underline is actually a reduced word, so it's a reduced expression for some permutation B, then actually, if you look at this walk up here, all that this walk is telling you is that B and your final flag are in relative position B. So in fact, all of the intermediate flags in this walk are completely determined by the final flag. So in this special case where your beta underline is reduced, you may as well only keep track of the final flag in your walk. So what I'm saying is that this braid variety is isomorphic to just the set of flags in the flag variety that are in relative position V with B and relative position W, not U, with the anti-standard flag. Then you look at this a little more, you realize that it has a very nice description. It's just the intersection of a Schubert cell BBB with an opposite Schubert cell B minus UB inside of the flag variety. And these are called open Richardson varieties. Come up in a number of contexts, including total positivity, and also if you want to compute Poisson-Lustig polynomials, might be interested in these varieties. Okay. There's an even more special case of this, which is where V, your permutation that beta underline is a reduced expression for, has a unique descent. And in this situation, these braid varieties are actually isomorphic to open positoid varieties. Okay, so I think these are not as well studied from like an algebraic geometry perspective, but they're very nice from a combinatorial perspective. They were introduced by Knudsen and Lamb and Spire, building on work of Kosnikov. And yeah, there's just like a lot of really nice combinatorics inside of these varieties. That's kind of another reason here. Okay, and then there's another special case that is nice, but it's sort of, I think you've only heard of these varieties if you care a lot about cluster algebra, so maybe I'll skip over what this. Okay, so those are my varieties. And the results I'll tell you about today, possibly in slightly abbreviated form since we spent some time with the.
No.
Okay.
There's T after that, so you just don't.
Oh, okay, great. All right, okay, so the result I want to talk to you about is this particular kind of combinatorial structure of these varieties. So I'll demystify some of these words later, but so the result is that the coordinate ring of one of these braid varieties is a cluster algebra. Okay, so I'll give you the details about what cluster algebras are in a second, but what you should think of is they are some commutative rings where all of the information of the ring is encoded in kind of an initial combinatorial object, which is called a seed. So you hand me a seed, which is some combinatorial information, and the cluster algebra is just completely determined by that choice of seed. Okay, so really what this is saying is that these coordinate rings are completely determined by some kind of relatively straightforward combinatorial object. And the particular combinatorial objects we're going to use are bicolored graphs, which are embedded in 3 space. So we call these 3D plabic graphs for historical reasons, basically. Plabic graphs, which are planar bicolored graphs, were used by Posnikov to study these positoroid varieties, and these are kind of upgradings of these planar bicolored graphs to bicolored graphs in 3D. So that's why they're called that. Okay. Yeah, so there are a couple of things I should say before telling you what a cluster algebra is. The first thing is, so this is a type A result. We've got general type work in progress. Another very important thing to say is there's another group of mathematicians, Casals, Gorski, Leshan, and Simmental, who have a similar result. So basically, they also show that this coordinate ring is a cluster algebra, but the combinatorial objects they use to obtain this seed are very different, and we don't know how they relate to ours. So yeah, so our techniques are quite different. I should also say it resolves a couple of conjectures and generalizes some previous work. So the conjecture was of Leclerc in the case of Richardson's. And finally, I should also say our work owes an intellectual debt to the PhD thesis of Ingermanson. So she was a student of David's who went into industry immediately after her PhD. So her PhD was never published, but we're kind of building on some of her ideas. Okay, so if you don't care too much about cluster algebras, this might not be a terribly exciting result. So let me tell you some corollaries that might make you feel more interested.
So I have a question.
Yeah.
So this conjecture by Leclerc is these categories of representations of lambda module.
That's right. Yeah. So yeah, that's right. So Leclerc's conjecture can be formulated in kind of categorical language, and in fact, yeah, his approach was very categorical. Our results, like we don't use that technology at all. Yeah, we kind of use purely analytic rings. Okay, so some results that we obtain, or some corollaries that we get. So what we show is that if you consider one of these braid varieties over a finite field and compute the number of points, you get a specialization of a certain term of the Humphrey polynomial of a link that you obtain from U and beta. So somehow these varieties are have some information about some links. Yeah, and we also prove some results about the cohomology of these varieties as well. And I'll just say the hope, which is not currently known but sort of expected, is that the cohomology of these varieties should be related to the Kavanagh-Brzezinski homology of these particular links. So yeah, this is sort of like, yeah, this is a hope. I don't think anyone has sat down and worked out the details yet, but yeah, another reason to be interested in these varieties is they give you access to some link invariants, and our results give some information in that direction. Okay.
Sorry, so you're saying the hope is that by understanding the cluster algebra structure of this might ease or facilitate the connection to Kavanagh-Brzezinski.
That's so more in the line of from the cluster structure, we understand some things about this cohomology. So in particular, there's what's called a curious Lefschetz phenomenon, which is some symmetry in the cohomology. And so if we know this relationship, then knowing that these guys have a cluster structure, that also tells you some symmetry in Kavanagh-Brzezinski homology. So yeah, kind of more along the lines of the cluster structure will then tell you something interesting about this, rather than having the cluster structure will actually help you prove this. Yeah, I'm not sure.
And somehow having the cluster structure helps you counting points. And
Yeah, that's
fields?
right.
Okay.
So this is very much, if you have a particularly nice cluster structure, which you do, then you can just sort of see the recursion of the Homfley polynomial on the level of the combinatorics of the cluster algebra.
Okay.
This is kind of using recent work of Galoshin and Lamb.
Okay.
Okay, so let me tell you now what is the cluster structure. So what is the cluster algebra? Okay, if you don't feel like paying attention to the details, that's fine. Just think of a cluster algebra as an algebra completely determined by this initial combinatorial information, and that will do you okay for the rest of the talk. If you do care about the details, let me give you some. So cluster algebras were defined first by Fomin and Zelevinsky around 2000. They were interested in understanding dual canonical bases and total positivity. Since then, cluster algebras have appeared in all kinds of fields, and very broad range of topics. So, okay, so I keep saying this cluster algebra is completely determined by this combinatorial information of an initial seed. So what is an initial seed? Well, it's a pair. The pair is, the first thing in the pair is what's called a cluster of cluster variables. So these are some algebraically independent functions. Okay. And then the second element of the pair is a quiver, that is a directed graph. And I'm going to decorate the vertices of my quiver with the functions. So here is an example of a seed. Just going to look it up. You'll see there are two different kinds of quiver vertices. Some are these little like ice cubes, and some of them are just dots. So the ice cubes are called frozen vertices, and those cluster variables are called frozen, and they're a little bit distinguished from the other ones. Okay, so this cluster is going to be a little tiny piece of the generators of my ring, and I need an operation to produce more generators. That operation is called mutation. So I'm not really going to tell you what mutation is, but it's an operation you can perform at non-frozen vertices of your quiver to produce a new seed. So you'll get a new cluster of cluster variables and a new quiver. So for example, in this quiver, I've only got one non-frozen vertex. And if I mutate there, I get a new seed with a different cluster variable sitting on top of that vertex. And also I've changed the errors of my quiver. Okay, and so all I'll say is what new variable shows up is completely determined by the quiver over here. So this monomial x2, x3 is there because x2 and x3 point into this vertex. And this monomial 1 is here because there are no arrows pointing out of the vertex. So there's some, like this is a very combinatorial and explicit process, this mutation. Okay, so you start with this seed, it gives you some of the generators. Then you mutate, you mutate, you mutate, you keep mutating forever. And that collection of all of the cluster variables you get by any sequence of mutations, those will be the generators of your cluster algebra. So this cluster algebra is the C algebra generated by frozen variables and their inverses, and all cluster variables that you got from your initial seed by doing arbitrary mutations. So in general, this is a list of infinitely many, actually the wrong polynomials. Okay, so this is kind of a funny way to define an algebra. Usually we have like a rather short list of generators and then maybe like many relations among them, which may be quite long. This is like you're defining your algebra using infinitely many generators, but the relations that you have among them are all kind of short. Okay, so let's do a little example. So here was the seed I started with. It turns out I only have one, I can only mutate to get one other seed, it's this one. So the cluster algebra I get is generated by the two frozen variables and their inverses, and then the cluster variables from each of the seeds sigma and sigma prime. Okay, and if you stare at this and are a certain kind of person, I don't know actually if anyone is this kind of person, you notice that this is the coordinate ring of a not too weird variety. That variety is, it's okay, it's not quite SL2, but it's SL2 circ. So the open part of SL2 where the off diagonal entries are not allowed to vanish. Okay, so this particular cluster algebra is equal to the coordinate ring of some variety. In this situation, we say the variety has a cluster structure. Any questions about this?
You really want to invert the frozen?
You really want to invert the frozens. Yeah, it feels like funny because we don't want SL2 circle, we want SL2, but for the rest of the machinery to work, it's kind of.
Is that like a double d orbit or?
Yeah, so it's the intersection of the big Bruja and big like opposite Bruja cell. Yeah. Okay, so that's called, yeah, it's a double Bruja cell as well. Okay.
But if you define like this, geometry is not clear, because a priori that you have a right about line type, you start like with a infinity many generators.
Yeah, that's right. So this is a hard thing, proving that your coordinate ring is equal to a cluster algebra. Like it's quite subtle.
No, but I mean, the other way, if you define the class variety the way you're doing, then you have when I'm starting writing, but it's not clear that it's finite type because you're defining it as having infinite many.
That's right. Oh, yes, I'm sorry. There are some results about when this ring is actually finitely generated. And which is often. Ian, do you remember exactly the condition? It's often that this thing is actually finitely generated. It's just that you've chosen sort of a stupid generating set. But yeah.
But it's not. So you're still saying it's not true generally.
Yeah, I think not. You can get something that, you can get something very poorly behaved. It's just no one thinks about those in geometric contexts, I guess. Yeah, so if you, in practice, what you do is you have a variety in mind and you want to identify that it is a cluster algebra or that the coordinate ring is a cluster algebra. You sort of rarely think about an arbitrary cluster algebra and then try to cook up the variety for it. Yeah. Okay. Okay, so maybe you want to think about this thing more geometrically. So here's another perspective. So say your affine variety has a cluster structure. Then what this tells you is that your variety is covered up to codimension 2 by some tori. What are these tori? Well, you've got one torus for each cluster, and the torus is exactly where the cluster variables in that cluster are non-vanishing. And if you think about it this way, then your cluster is actually a distinguished choice of basis of characters of your torus. And so the content of having a cluster structure is like, very roughly, you have all of these tori and you can kind of simultaneously choose distinguished bases for them in a very nice way. Okay, so, and kind of the nice way is encoded in this combinatorial information of the quiver. Yeah, so if you want to take this alternate perspective, this quiver Q, it's telling you about some relations on your variety, and it's also encoding maps between these cluster tori.
If I use the word simultaneously, my rough understanding was that you have this, you have indeed a collection, a very large collection of tori. Each of them has their own preferred set of generating characters. And then there's some gluing relations, which are these mutation relations, which say how to relate the regular function from one towards the regular function to the other.
Sure.
But it's not like any given element is you have a basis of all of the tori together.
Yeah, I guess not. So it is true that it is true that any character of one cluster torus is a Laurent polynomial in the clusters, like, sorry, what am I saying? So there's this cluster algebra is contained in the Laurent polynomial ring of the initial cluster. That's what I'm trying to say. So this is a non-trivial fact. So what I'm saying is if you pick any given cluster, any regular function on your variety can be written as a Laurent polynomial in that cluster. So in some sense,
But not just rational, not just arbitrary rational function.
That's right. It's actually
It's a regular function. It's the regular function on the original.
That's
on
right.
the original torus.
Yeah, that's right.
I see.
Yeah, so there is like some sort of compatibility here. I don't want to get too precise, I guess, about.
No, I think so. But this is not. But then the term you used was perfectly appropriate. No, because you're saying that they all live in the same.
Yeah, that's right. In the same Laurent polynomial ring. Yeah. Okay. All right, so if you want to think about it this way, then for this like SL2 circuit example, you have two cluster tori. The first one is when these elements are non-zero, and the second one is when these elements are non-zero. And you'll see, of course, like I'm really only covered up to codimension 2 by the cluster tori. I don't cover everything. Okay. So that's this cluster stuff. So you can see when I said that the seed was just combinatorial information, I was kind of lying. So this part of the information of the seed is, well, it's geometric, right? I'm identifying a torus for each, right? The seed is, I'm picking a torus, and I'm also picking a distinguished basis of characters on that torus. That feels pretty geometric. And then the combinatorial part is kind of, it's really in this directed graph Q, right? It's just a directed graph. So that is kind of like honestly combinatorial information. Okay, so for the rest of the talk, I'm first going to tell you about this geometric information for the braid varieties. So what are my cluster tori? What characters do I pick? And then I'll tell you about this combinatorial information of what is the quiver that you get. Okay, so, oh, I guess I should also say, so some reasons why you might care about a variety having a cluster structure. It endows the coordinate ring with what's called something you might call a canonical basis with positive structure constants. So having a cluster structure kind of automatically gives you this nice basis for your ring of functions. And you also, just from having a sufficiently nice cluster structure, you know some stuff about the cohomology of your variety. That's the result of minus five. So that's two reasons you might care to prove your variety has this. Okay, so let me tell you about the tori, some of the cluster tori we get for the braid varieties. Okay, so remember our braid varieties look like this. So right points are these walks where I've constrained the directions of the steps and also where I end up. Okay, so I will give you one cluster torus for each braid word beta underline for my positive braid. There are more cluster tori, but these are the ones that are kind of easy. And we call them Deodar tori because they're really inspired by a classical stratification of Richardson varieties due to Deodar. Okay, so to describe this, I also need a combinatorial notion called the Demeasure product. So if I have, okay, so if I take the Demeasure product of V, a permutation, and SI, so I do V star SI, it is either the normal product, V SI, or it's just V, and I pick whichever one is higher in the group. Okay, so the Demeasure product, you should think of it as like normal product, except I'm only allowed to go up in the group. Okay, so what is this torus? Well, in words, kind of intuitively, it's all of those walks where if you start at the last flag and move to the left, you always greedily increase your distance from the anti-standard flag. Okay, so what do I mean? So, okay, we've started at some, okay, so our walk ends at some point. Now, if I look at the second to last flag in my walk, I've only changed the IL subspace. So the only possibility for this position, well, it could either be W, which was this position, or it could be W times SIL. And this in this torus, I always need to pick the bigger of those two permutations. Okay, so just a quick example down here. So what's the torus for this particular choice of braid word? Okay, so my last flag in the braid variety, it's in the identity position with the anti-standard flag. Okay, so then I change the I1 subspace, and whatever goes here, the position to the anti-standard flag, it needs to be the bigger of identity times S1 and identity. So the bigger of those two is S1. Okay, and then I take the next step. So I want to know what permutation should I put here. It needs to be whichever is bigger, SI times SI, or just SI. Okay, and the bigger one's SI. Okay, and then at the next step, again, kind of my length can increase, so it does. So I get S1 to S2. And then at the next step, my length can again increase. Okay, but then at the step after that, I've already gone to W naught, so I'm So it would have just kept being W naught if I extended it. Okay, so that is the torus. It's just defined by this greedy condition. Okay, and there's a little bit of terminology I need. So you might think, kind of looking at this torus, that all of the flags along the way are equally important, but there are too many of them. And so we kind of need to ignore some of these flags because we have more than dimension any work of flags. And so I'll give you the condition. These are the ones you ignore. Well, okay, so I guess I'll tell you the ones you keep. So if you have a little triangle in your torus and you see the same permutation on these two edges, then this is sort of an important crossing. So we're going to call it a solid crossing, and we're going to pay attention to that one. If you're in a triangle and you see different permutations on these two edges, those are called hollow crossings, and we're kind of going to ignore them, or they won't be as important in the construction. Okay, so I'm going to highlight the hollow crossings so you remember to ignore them, I guess. So here on these two edges of the triangle, I see different permutations. So this is a hollow crossing. The next triangle, I see the same permutations, that one's solid, and then this one is hollow, and the last one's. Okay, so if you don't want to think about this business of, oh, do I see the same or different permutations on the triangle? The hollow crossings actually just form the rightmost expression for the permutation to use in your word. So there's like a really easy way. Yeah.
Is that obvious that this is torus?
Yeah, so it's not well, it depends. So it turns out that, okay, so let's focus on one of the like solid crossings. It turns out that if you know what this flag is already, there's C star worth of flags you can put here. If you have a hollow crossing, if you know this flag, actually this flag is completely determined. So for each solid crossing, basically I have a copy of C star, and for each hollow crossing I've got a point. So that's kind of why it's a torus, and that's why it's a torus of the correct dimension, which is length of beta minus. Yeah, that's a great question. Okay, so this is a cluster torus, turns out. So now I need to tell you about this distinguished basis of characters. And
so these tori, they are determined by the collection of solid and hollow processes.
yeah, that's right. Or I guess I get one torus for each braid word. And once I have the braid word and I've already picked my permutation U, then that determines the solid processes. And like I said, this is kind of really just a souped up version of the Deodar stratification of Richardson varieties and the Deodar torus. Okay, so right, so I got my torus. Now let me tell you about this distinguished basis of characters. And I'm kind of always glad to do this part in front of a geometric audience rather than a combinatorial audience, because I'm going to give you a geometrically very satisfying answer and a combinatorially like kind of bad one. So how do I get this distinguished basis of characters? Well, I'm going to look at the complement of my Deodar torus in the braid variety. And this just decomposes into a bunch of irreducible hypersurfaces. It turns out one hypersurface for each solid crossing. Okay, and it's really easy to describe what the hypersurfaces are, but I'm going to skip it. I will just tell you what is my cluster variable. Well, they're going to be indexed by the solid crossings. So C is a solid crossing, and the cluster variable XC is just the torus character that vanishes to order 1 on the corresponding hypersurface and order 0 on all of the hypersurfaces. Okay, so it's like really, it's a kind of like a geometrically very natural thing to do. This is kind of exactly the basis of characters that you would think of. Okay, combinatorially, why it's not so nice is that I haven't actually provided you with any formulas for these cluster variables, so if you want to do computations, it might be a bit messy. Okay, but I should say there is a way to produce formulas for these cluster variables, it's just too long.
So the rank of the tori is the number of solid crossings.
That's right. That's right. Okay, yeah, and I should say I'm lying a little bit about the details, but in spirit, I'm saying the correct thing. Okay, So that's my distinguished basis of characters. So that's the torus, so that's the geometric information. And now I need this combinatorial information that tells you how to go from one torus to the next, right, via this mutation. And right, so that is a kind of purely combinatorial problem. And so let me give you the outline of what I'm going to do. So at the end of this, I need to get a quiver. But I'm going to take a kind of detour into bicolored graphs. So starting from my braid word, right, that gives me a torus. I'm going to produce, using a wiring diagram, some bicolored graph embedded in 3 space with n marked points. Okay, and each solid crossing, which corresponds to a cluster variable, I'm going to turn into a relative cycle in my graph. Okay, and then I need to get a quiver out of this. And basically the quiver is just going to record how the relative cycles interact with each other. But I don't want to do this on the graph. I actually want to upgrade my graph to an oriented surface with boundary. Then I've got a bunch of cycles on this oriented surface, and I can just compute signed intersection numbers. And those signed intersection numbers of cycles, that's what will give me the arrows. Okay, so that's the outline, and then I'll give you some details about actually how this construction works. But I guess any questions about the outline? I will go through the steps then as threatened. Okay, so let's look at this particular example. So this is my braid word, and my U here is W naught. So first, let me identify the hollow crossings. Remember, that's the like rightmost sub-expression for U. So that looks like this here. Okay, so to get my bicolored graph, the first thing I'm going to do is draw basically the wiring diagram of my braid word, except it's actually the braid diagram because I don't want to think about this in a plane. I want to think about it in 3 dimensions. So, but it's just like the wiring diagram, right? It's just that I actually am going to think of, you know, this strand is going to cross above this strand in 3 space. Okay, so I just draw the wiring diagram, and I also want to mark the hollow crossings here. And then how do I get a graph? All I do is I take each one of my solid crossings and I just replace it with a little white black bridge. Okay, so really easy, right? So I just take this and I replace it with a little white black bridge. Okay, and I also add marked points on the left endpoints of all of my strings. Okay, so that's the bicolored graph. It's 3-dimensional, right? Because I have these places where I've got these crossings, so I need to think about it embedded in 3D. I can't draw it in the plane without crossings. Okay, so this might seem like very mild to you so far. And so where things get a little bit weird is when you introduce these cycles. So the cycles are corresponding to cluster variables, and interactions of the cycles will give me the quiver. So how do I define these cycles? Okay, the easiest way to define them is actually to define certain disks or soap films in my graph that are bounded by the edges of the graph, and then the cycle will just be the boundary of that disk. Okay, so I'm going to have a disk for each solid crossing. So for each black-white bridge like this, my disk is going to start at that bridge and kind of cling to these edges of my graph as it moves to the left. And then it's going to propagate all the way through my graph following these rules. Okay, and these are really hard to just stare at and understand, so let me just do an example. So let me think about this solid crossing. So what does my disk look like? Well, it starts at that bridge, and it kind of clings to those edges of my graph. And then I'm approaching another bridge 6, and it looks like this scenario. So actually my disk is just going to end at 6. So in this situation, okay, my cycle is the boundary. So in this situation, the cycle is just these edges of my graph. Okay, so not that exciting. So let's do another example. Maybe the cycle or the disk for 6. Okay, so in this situation, the disk starts like this. It clings to these strands. It passes under that crossing 5. And then now I'm approaching this bridge 4, and the situation looks like this one. And so the disk sort of passes underneath that bridge, and it keeps going. Okay, and then at 3, I see the same thing. So again, it passes underneath. And then it's kind of clinging to the bottom strand of this crossing. And then it goes like that. Okay, so this disk is not really honestly a disk, and so the cycle that is its boundary is actually a relative cycle. That's okay. So the cycle I get is on these edges of my curve. Okay, and I should say, remember we have these like frozen versus mutable vertices, and you can see this already at the level of cycles. If your cycle is honestly a cycle, then that's a mutable cluster variable, and if your cycle is a relative cycle, then you've got a frozen cluster variable. Okay, so that's how I get the cycles. And you can actually stop here and just look at the cycles on the graph, and there's like an algorithmic way to compute the quiver from this. You look at the edges 2 cycles have in common, and you kind of flip them stuff around and do some counts. And yeah, so you can get the quivers just from this picture, but it's a little bit nicer to pass to the surfaces, and then you can just compute it kind of in a normal way, just using signed intersection. Okay, so oh, I guess before we do that, I wanted to talk briefly about some special cases. So remember, I told you there were some nice special cases of braid varieties, the Richardson case, and then even more special, the positroid case. So what's going on in these nice special cases? Well, in the positroid case, the construction simplifies a ton. So here's an example of the kind of 3D plabic graph I'd get in a positroid case. And I've also drawn one of the disks. So it looks kind of big and horrible. It does something, you know, I used one of the weird propagation rules here, etc. But it turns out if you take this picture and you just delete the tails of every wire. So by tail, I mean, I start at the right endpoint of the wire and then I trace it until it hits its first bridge. So if I delete all of those, I actually get a planar graph, and my disks just cover a single face of the planar graph. And the planar graphs you get, they're actually special. They're called reduced, and they're studied by Posnikov and many other people. So these kind of have already shown up in the literature. They're very nice to work with. Okay, so in the positroid case, you could rephrase our construction in a much simpler way. But unfortunately, even in the Richardson case, you can't do this. So you kind of need the full power of the construction. So this is just to say, so here's a Richardson example, and here's one of our disks. And if you played the same game as in the positroid case where you just delete tails, well, in this example, you get something planar, you don't always. And this disk, it covers more than one face. So we need some mechanism to predict that. So this is just to say kind of the positroid case is super nice. The Richardson case is already complicated enough that you need this more general construction. And then braid varieties, basically the same construction works. So it's just like, oh, we do the fullest generality that our methods can. Okay, so now let me just quickly talk about how to get to a surface. It's pretty straightforward. If you're a certain kind of person, I can just say, oh, you make the bicolored graph into a ribbon graph and look at the associated, like naturally associated surface, and that's all you're doing. If you're not that kind of person, this is the transformation I'm doing. So I look at a little neighborhood of each white vertex, and I replace it with a little snippet of a surface, oriented surface that looks like this. Oh, and I guess I'm missing an orientation, so this should go okay. Okay. And around, I take a little neighborhood around every black vertex, and I replace it with a little snippet of a surface that looks like this. So this part is the underside of the surface. And then, okay, so I've done that local replacement here. And then I just connect the little surface fragments along each edge of G. So I go like this. I'm not going to do all of these because they're very boring. But this bit will pass under, and etc. Okay, so another way to think about this is you're taking your graph and you're fattening the edges into little ribbons, and then the ribbons glue in a prescribed way around each vertex. Okay, and now your cycles, which were cycles on the graph, are cycles on this surface. So here's a picture. So here is my oriented surface with boundary and some mark points, and then drawn on it are all of the cycles. So like this is the cycle for 7 that we computed. This is the cycle for 6. And the way you decide the number of arrows between two vertices is you just look at the signed intersection number of the corresponding cycles. So it's a little hard to see because I drawn badly, but here we have an intersection point of cycle 3 and cycle 4. Here we've got an intersection point of cycle 6 and 7, and because of the orientations, kind of 3 and 6 play the same role over here, and 4 and 7 play the same role. So we've got kind of one arrow from 3 to 4 and one arrow from 6. Okay, so that's the quiver. And oh yeah,
Can you get arbitrary quivers? No, if I take my favorite quiver,
can you get it like this? I think you can probably embed an arbitrary quiver into one of these quivers. I'm not sure if I could get an arbitrary quiver kind of on the nose. I think this is a result of oh, I'm so sorry, of Agusa, and someone else. They showed that like if you just look at all plabic graph quivers, this is like a really, really general class of quivers. So you sort of like, yeah. So I guess I'm not sure, but I do think it's a fairly broad class of quivers that was. Yeah, okay. So let me just summarize, because I won't go maybe too much over time after all. So the main theorem is that this coordinate ring is a cluster algebra. And how is this cluster algebra defined? Well, I need to tell you a torus and some bases of that torus. My tori were these Deodar tori defined by greedy procedures. My basis were the functions defining the Deodar hypersurfaces, so the complement of this torus. Okay, so that was the geometric information. And then the combinatorial information was, I started with my braid word, I turned it into a graph, and then each one of my solid crossings, or each one of my cluster variables, corresponded to some cycle in this graph. And then I just recorded the interactions of these cycles, and I gave them. And just to remind you, one of the corollaries we get actually from this part, the construction of the quiver, is that the finite field point count of my variety recovers some of the Hompley polynomial of a particular length, which I didn't tell you, but it's closely related to the braid beta. And then we also, using results of Lamb and Spire, get some symmetry results for the cohomology of this variety. And exactly what that property is called Shurius-Lefschetz. I'll refer you to the paper for the exact statement. Yeah, thanks so much for listening.
Question?
What is it like about a variety that would lead one to expect there's a cluster structure?
Yeah, that's a really good question. So one thing is if you can just easily identify many open tori, that's an encouraging sign. Like, because you should have lots of open tori floating around. So if it's hard to identify even one, not so sure. The other thing is that, okay, so I didn't really tell you what mutation does, but mutation is basically the prototypical kind of mutation is actually just using a classical determinantal identity. So either like the Dano-Jacobi identity or like a 3-term Cooper relation. Those are sort of like the prototypical things you're using in a mutation. So if you're in a variety which has like a lot of determinantal, where functions have a lot of determinantal identities, or you can just sort of easily spot many 3-term relations, that is also a good sign. Yeah, it's actually, I mean, it's kind of hard to actually show that a ring is a cluster algebra. So yeah, I think there's no like there's like sort of artisanal techniques or something. It like depends a bit on exactly what you've got.
Yeah. Okay. Follow-up question. So I know very little about cluster algebras, but what I thought was true is that if it's finitely generated, then it's like Dinkin type. It's associated with the Dinkin power.
Oh, so yeah, this is a good
not true?
question. No, so it is kind of true. So when you have a ring and you identify that it's a cluster algebra, you're kind of, the cluster algebra is telling you some generators. And sometimes those generators are a very inefficient generating set. So sometimes, even though the ring is finitely generated, the cluster algebra structure is telling you infinitely many generators. The Dinkin situation is when the cluster algebra is smart and only tells you finitely many generators.
Okay, so I can still get a finitely generated algebra, but the cluster thing is infinite.
That's right.
So that's what happens here.
That's right. And that's what happens most of the time. So yeah, sometimes you only have finitely many cluster variables. This is a very special situation, and the quivers will always be orientations, or you can always choose your quiver to be an orientation of a Dinkin diagram, a finite tape. Yeah, but most of the time the cluster algebra is sort of like, well, I guess I shouldn't say it's not that smart. It cares about something different, right? The cluster algebra actually cares about producing this basis. The cluster variables will be part of this basis, and so sometimes this basis is very big and complicated, and you need lots of, you kind of need lots of things to describe it. So it's pretty simple.
Great, thank you.
Yeah.
I guess, so this is, you described the, what you get from one and Deodar torus for, beta, but then you have these braid moves. So like,
That's
are like all the seeds coming from other, from.
Oh yeah, that's a good question.
Okay.
Yes, so the braid moves either do nothing, so maybe actually two of my Deodar tori coincide, or they will do a mutation.
Okay.
Yeah, so all of so for a fixed braid variety, we produce a number of Deodar tori, and they're all related by mutation.
Okay.
Yeah.
Have you tried to construct some kind of Newton curve bodies with your 3D baby graphs, like a 3D version of what each and really have?
Yeah, we have not, but that's like a really, it's a very good question.
Like there's a construction of Newton curve bodies in the planar case by Lauren Williams in Cambridge. So I was wondering whether there was an upgraded version of this.
Yeah, I mean, that's a great question. Yeah, sort of, we, I guess what I should say is we defined 3D plabic graphs and kind of know exactly as much about them as we needed in order to prove this result, but there's certainly like many combinatorial questions you want to ask, kind of exactly how much of the planar case generalizes.
Right.
Yeah, and we sort of don't know. One thing, okay, so one thing I guess I will say is, in the planar case, it's very natural to associate a function to each space. Or no, I guess I've already said, yeah. So the obstacle is kind of, in the planar case, the disks that we create corresponding to cluster variables, they're sort of just single faces. And so it's sort of easy to understand what you get. In the non-planar case, they're just some disks in 3 space. They might intersect each other in funny ways. Yeah. So it's just a much more complicated combinatorial problem. Yeah. So sort of you kind of think that maybe interactions of disks telling you something about functions, and you would then want to use those functions to make these Newton-Cohen bodies, and yeah, so probably.
But you may have a kind of evaluation like G vector type evaluation and correlations on that.
I mean, you definitely have G vectors.
Right.
You get that automatically for any cluster algebra.
And they are meaningful in the 3D. I mean,
I'm like, are they interpretable immediately in terms of this graph?
Yes, or the 3D graph.
Oh yeah. So maybe I should pass to this picture, or maybe this one.
But I mean, as far as I can remember, in their evaluation is so what they do with Richard Williams is some kind of monomial valuation, which looks like kind of G vector, right? So you could do that, right?
I don't know. I mean, I don't remember their construction very well, but I remember the valuation is really easy to interpret if you label all of the faces by like Young diagrams. I just don't know how to. It just doesn't kind of work as easily here because the functions are really functions on flags, like complete flags rather than just like the k-step piece. So yeah, maybe you'd want to label each face with like a mutation instead of a Young diagram. I'm not sure. Yeah, it's a really good question.
Could you say something about the partial flag variety testing?
Oh yeah, so I guess all I can really say is sometimes your open Richardson variety is a subset of the complete flag variety. but sometimes you get lucky and it actually projects isomorphically to a partial flag variety. And so I think in that situation, okay, so the pository varieties are sort of exactly the open Richardson varieties that project isomorphically down to the Grossmannian. And which Grossmannian you can figure out by knowing where your permutation has a descent. I mean, I can tell you which open Richardson varieties should project isomorphically to like some other Gmod P, but I can't tell you kind of anything more about them, except that they're also, I mean, they're open Richardsons, but they're special cases of this story. Yeah, so the V's you should choose, so you pick your partial flag variety Gmod P, you look at the corresponding parabolic subgroup of Sn, or sorry, parabolic quotient of Sn, and then kind of want your V's to be in that parabolic quotient. Yeah, and the partial flag variety will be stratified by these projected open Richardsons of that sort, but that's sort of all I can say. Yeah.
And is some or most of all of this expected to work in arbitrary impact? We define it very right for.
Yeah, so we are working on the general type paper, basically all of the geometric content. So this stuff is not type dependent. The ability to draw this graph seems to be type A because you have wiring diagrams. And yeah, it's sort of not clear. Yeah, sort of not clear what the combinatorics of this would be. Instead, you kind of rephrase everything in terms of some like purely algebraic language. It's kind of a familiar type A versus general type dichotomy. You just can't do as much combinatorics. Yeah, one thing I will say is that the other group with similar results, which uses, but they have like very different combinatorial objects here, their combinatories does seem to work in arbitrary type. So that's very interesting. Their objects are algebraic weaves. If you ever hear
Algebraic
weaves.
weaves.
That's right.
So, so each, okay, so mutation, does that have a combinatorial, is it, like if I take a 3D plabic graph, so that you're saying that generates a seed?
Yep.
If you mutate, is the result still described by a 3D plabic graph?
Yeah, so some mutations.
Some, but not all.
Not all. So if one of my cycles is kind of like a square, so that means, right, so I picked this particular drawing of my graph in the plane from the wiring diagram, and if one of my cycles just bounds a little square face of that drawing, then mutation there, the new seed will be given by another one of these 3D plabic graphs. If I take some like really big cycle, which I don't have any examples of here, but if I take some really big cycle and I mutate there, the resulting thing I cannot describe in terms of a 3D plabic graph.
Are you hopeful that there's some larger class of combinatorial things which is preserved under the mutations?
I mean, not that hopeful. Basically, there are very few cluster algebras where there's like good combinatorial control of all seeds. Like this is a pretty tall order.
Okay.
Yeah, so I think in most situations you're satisfied with a good combinatorial understanding of like the nicest seeds. I mean, the point is sort of your cluster algebra is controlled completely actually by one seed, right? Because from one you can get the rest. So it's sort of like, well, as long as you have like kind of a few choices for that one seed, it's kind of usually good enough. Yeah, so I only know of one class of cluster algebras where you have combinatorial understanding of like infinitely many seeds.
Okay.
Thanks, Melissa, for a great talk.